Lunch and Learn is an MFG radio network production brought to you by GIE Media's Manufacturing Group. We highlight some of the latest innovations in manufacturing and design to help you gain insights to the newest products and technologies in the medical, aerospace, defense, and electric vehicle manufacturing industries to keep you ahead of the competition. Hello and welcome to the latest Manufacturing Lunch and Learn from GIE Media. I'm Jake Kaufman, Senior Editor for the Manufacturing Group of magazines here at GIE. We're so happy to be joined today by Open Mind as they'll discuss efficient CAM toolpaths and how they're key drivers for machining productivity and accuracy. Open Mind is one of the most sought-after developers of powerful and innovative CAD/CAM solutions for machine and controller independent NC programming. Today's presenter, Ernie Dickinson, the technical sales for Open Mind. But without any further ado, Ernie, the floor is all yours.
Hello, everyone, and welcome. Automation is all around us, from our smart homes that adjust lighting and temperature automatically to self-driving cars that require no input from the user. It's become an integral part of daily life, and there is no avoiding it. Even in the world of precision manufacturing, a world steeped with tradition, automation has made a strong impact, improving accessibility and efficiency. But here's a key point. Automation is only as good as the input it starts with. If you automate a poor process, you don't solve the problem, you just end up with bad results faster. And in other words, if you automate garbage, all you get is automated garbage. My name is Ernie Dickinson, and I'm here to tell you that even in a rapidly automated world, there is still space for creativity and progression. And that creativity and progression will only make CAM automation a more powerful tool for the future of manufacturing. About a year ago, while casually browsing the internet, I came across a quote that really struck a nerve. It implied that toolpath development was essentially complete, that with automation there was nothing left to improve. Now, working at a CAM company and seeing the level of innovation, effort, and precision that goes in creating safer and more efficient machining strategies, I found that view surprisingly narrow. And I'll admit, I took it a little personally. Sure, automation is a major force in manufacturing today, and for good reason. It boosts efficiency, reduces errors, and opens up new possibilities. But to say it's the end of the road for toolpath development, that couldn't be further from the truth. What I see every day are new creative ideas, advancements in adaptive strategies, smarter tool engagement, and intelligent stock handling. They may not look like automation at first glance, but they're actually feeding the automation and pushing it forward. So that quote didn't just miss the mark, it missed the bigger picture. We're not at the end, we're at the edge of something even more exciting. Toolpath development is still evolving, and automation is just one part of a much larger ongoing story. But before we get into the point of this presentation, let's have a quick introduction to who we are. Open Mind has been solely focused on developing advanced CAM strategies for over 30 years. Our mission is to support the machining of high-end, high-precision, and high-value components. Our innovation comes from two key sources: the external input of customers and partners, and the internal drive of our own team, fueled by a passion for pushing the boundaries of what's possible in CAM. Customer feedback is incredibly valuable too, but it often leads to incremental improvements or even patch-style solutions. By balancing user input with our own forward-thinking ideas, we are able to innovate in ways that go beyond immediate needs. After all, while the customer may always be right, they don't always know what's possible, and that's where we come in. Input and collaboration with our machine tool partners extends our field of view with development, and it's not only valuable for pushing the software forward, but also for getting exposure to a much wider audience. I would imagine that most people first heard of us from our somewhat viral machining videos that we have done with our many machine tool partners. These include the Hermle Eagle, the Grove basketball hoop, and of course the widely known motocross helmet that was done in conjunction with both DMG and the customer. This partnership is bidirectional though. We provide a proven and extensive CAM solution to cover the many unique parts of machine tool applications you would encounter, and in turn, we can test new and upcoming technology on the latest and greatest equipment that's available to us. So a little bit about where we've been as an industry. Like many technologies, CAM has evolved significantly over time. Early on, most systems were limited to 2.5D machining, and if you were lucky, you could machine surfaces, starting with the ability to machine a single surface at a time. Back then, that was considered cutting edge. Then, the industry made a major leap in how toolpaths are generated. Instead of working surface by surface, we can now generate toolpaths that span multiple surfaces in a single pass using projected cell toolpaths, or Z-level slicing. What made these toolpaths even more powerful was the ability to do slope-based machining. This means we don't have to define machining boundaries manually. The software reads the part's geometry and intelligently applies the right strategy based on part topology, improving both productivity and part quality. As technology advanced, so did our capabilities. And once again, it felt like the possibilities were endless, or at least until the next big breakthrough came along. But as computer power improved, we were able to start increasing not only functionality, but also performance. Some would refer to this as feature creep, where every software release would take advantage of whatever computer power was accessible at the time and match it with functionality. More computing power would mean more features could be added, but not too much that the currently available hardware could not keep up. Toolpath calculations that would normally take programmers overnight or even over the weekend to finish were now only taking minutes. This opened up a lot of flexibility for what a toolpath calculation could do. Now, on top of just creating paths over a specific shape, we could check for gaps in the surfaces, check for collisions with other aspects of the tool assembly, and also get creative with boundaries. This was progress. Moving forward, the industry as a whole added options like high-performance roughing for difficult materials, better toolpath layout to be able to exactly match geometry conditions, and smooth toolpath transitions that would take advantage of the newer high-speed machines that were becoming more common at that time. All of these incremental progressions, as well as hundreds more, were added to not only make programming easier and safer, but to also increase the level of complexity in the machine components, as well as decreasing cutting times. Better CAM equaled better parts. As 2D and 3-axis CAM increased in power, the ability to safely create toolpaths with an additional vector component became a focus. 5-axis machining was in its early stages. Initially, tool direction was driven by the surfaces themselves, as seen in early 5-axis methods like swarf cutting or top milling. For example, the image on the left illustrates our 5-axis shape offset roughing toolpath. The tool orientation for a strategy like this is driven off the bottom of the surface that it's cutting, and the tool always stays normal to that surface. The true breakthrough came with the ability to combine proven 3-axis and 5-axis toolpath strategies while independently controlling tool orientation. This eliminated the dependency on surface normals for direction, opening up new capabilities. Complex mold and die projects, often involving surfaces with drastically varying orientations, became much more manageable. Furthermore, the addition of collision-aware tool orientation adaptation enabled the use of shorter, more rigid tools, even in deeper cavities. By dynamically tilting the tool away from potential collisions while maintaining optimal cutting conditions, we significantly reduced tool deflection and improved surface finish, ultimately unlocking efficient 5-axis simultaneous machining of intricate geometries previously considered too risky or too inefficient. It was clear that the more intelligence we could integrate into the toolpaths, the more that they could be pushed. One such example of this is the ability to automatically extend surfaces in the toolpath itself. This has been a recent addition for us and is a simple checkbox in value. No extensive CAD work is needed. And not just simply extending the surfaces, we are automatically feathering the toolpath itself when blending into another cut, assuring a smooth transition between machined areas. Think about it. What was once a very manual process of creating ramp surfaces so that the tool doesn't start right on the model is now pretty much automatic. This was always a very time-consuming part of the programming process. It could easily lead to human error. We are now able to not only extend, but we can automatically smooth out transitions. We have truly reached a point where the toolpaths are very automatic indeed. Some of the advancements in recent years are a bit more nuanced though. How often does a CAM programmer consider point distribution? If you care about the quality of your surface finishes, you really should. To explain this further, most CAM systems in the early days of programming would allow you to put a toolpath on surfaces, just like we spoke about earlier. But if you had the ability to do multiple surfaces, then you may have the unfortunate opportunity to have the cutter fall into gaps between these surfaces, if the surfaces were not mathematically perfectly aligned. This would create a gouge in the machine part that would either ruin the part, ruin the cutter, or perhaps even both. Then the industry collectively switched to calculating toolpaths not directly on surfaces, but on a watertight, tessellated mesh model of those surfaces. This would assure that there were no gaps for the cutter to fall into. The downside of this is that in very high surface requirement situations, the tessellation could be seen in the machine surface finish. Hypermill has come up with a simple and clever way of still checking against the watertight mesh model, but assuring that the toolpath is placed on the original mathematical surface model, guaranteeing a high quality surface finish every time. This is just one example of some of the power of controlling the output points, and there are many more examples of where and how program points are distributed can affect the machined outcome. As I mentioned earlier, toolpath development can come from several directions. Another important influence are the cutting tools. Sometimes new developments in cutting tools open up new opportunities for creative ways to use these tools within a CAM system. A couple of examples of this is the ability to use deburring brushes for internal hole deburring. In this case, OpenMind developed a specific cycle for these very unique cutters. It's important to note that this can work in both directions. For example, the idea of using modern barrel cutters came from an OpenMind employee who then took the idea to a tool manufacturer for them to make. So, in this case, instead of us reacting to a new type of cutter, the cutting tool companies reacted to our ability to create toolpaths in a specific way. This is also an example where a clever idea came not from customer input, but just plain old creative thinking from an internal engineer. So now we have the almost unlimited ability to pick and choose where and how we apply toolpaths on a part, totally gouge-free, trimming against stock models, and having intelligence to know where a larger cutter could not reach. Maybe smart toolpaths is a better term to use here. In the end, the more toolpath-specific automation you could build inherently into the toolpath itself, the lesser the load is on the system's automation. Automatically pre-finding areas for rest machining or edges for deburring is one less thing to worry about when creating automation scripts. In some ways, this feels like we've achieved peak toolpath perfection, but why not keep going? Why not continue making these toolpaths smarter and cooking in some of the automation directly into the cycles? If you're standing still, then you're only going backwards. So let's start talking about automation. In Hypermill, our automation is structured on one particular aspect of our software that has been around for over 20 years, our feature and macro technology. This technology comes standard with the core product and allows users to automatically search for specific geometry like holes, pockets, and surface groups, and then apply preset toolpaths to the selected geometry. One could look at this as automation light, and it's the first steps to creating a robust automation project. Even without our automation controller, a user can create simple solutions for doing multi-step hole procedures, efficient pocket machining, and surfacing with only a minimum number of mouse clicks. Once again, this isn't new technology for us. This has been around for a very long time. So now that we've seen how much automation can be integrated in the various parts of toolpath creation, and we spoke about the base of geometry selection and applying toolpaths, our feature and macro technology, the next step obviously is connecting all those pieces into one cohesive system. The real power of automation lies in its ability to capture and apply your expertise, embedding your knowledge directly into the process. What we need here is a scalable solution, one that could be as automated or as hands-on as the situation demands. Our Automation Center allows a user the ability to create efficient workflow for any part imaginable and have full control on what happens when. This can be as small as a simple startup routine that involves loading a file, creating a stock model, and then having a vice close on that stock model. Or it can be a complete automation, where once the part is loaded, the automation takes over and creates complete job lists of toolpaths for the user. Anything is possible. One other aspect of this automation that we haven't spoken about yet is the automation of not only the CAM, but also the CAD features as well. Any seasoned programmer knows that in many ways, having powerful CAD tools at your fingertips is as important as powerful CAM, and they truly do go hand in hand with each other. By extending the automation beyond just CAM into all supporting CAD tools, we unlock a significantly more efficient and streamlined workflow. Of course, automated CAM is all about applying toolpaths to geometry without manual input. But what happens when a standard cutting tool can't handle a specific feature, like a pocket that's too deep, or a corner radius that's too tight for a specific cutter? That's where our Hypermill virtual tool becomes essential. This tool allows automation developers to define conditional logic tied directly to the tool assemblies, including the cutter, holder, and any extensions. Based on those conditions, the system can automatically swap out tools or holders to suit the geometry, all without human intervention. In short, the virtual tool helps us automate not just the toolpath creation, but also intelligent tool selection, making the entire CAM process more adaptive and reliable. One thing to keep in mind, automation does not mean error-free. Automation is still driven by humans, and of course, humans can always make mistakes. This is where the Hypermill virtual machine comes into play. Having an effective and powerful simulation tool based on accurate digital twins that can backstop the automation is critical to process security. This tool should be closely tied to the actual machine tool, assuring all movements are checked for potential of collision, whether these movements are cutting or non-cutting. This should ideally be done on the posted G code and not on the intermediate CAM data, if at all possible. Virtual Machine, and specifically the Virtual Machine Optimizer, can make sure that all cutting motions are as smooth as well as creating smooth non-cutting or linking movements. Confidence is the key here. What good is automated CAM when a user has to stand at a machine with their hand on the e-stop button for every part or every first run? Remember, automated garbage is still just garbage. Some of the advanced features of Virtual Machine include having an automatic search for alternative solutions. If tilting your trunnion in one direction causes a collision, then Hypermill Virtual Machine will find an alternative solution and tilt it in the other direction. Also, the Hypermill Virtual Machine does automatic linking. These linking movements can be in 2D, 3-axis, or 5-axis jobs, and they're checked against the machine model. Optimization of clearance planes is also done by the virtual machine, keeping the tool as close to the part as possible, eliminating any air cutting. And of course, if your machine requires rewinds, Hypermill Virtual Machine will automatically generate these rewinds when necessary. Hypermill is now blurring the boundaries between simulation and toolpath calculation. We are giving users more control by integrating machine kinematics directly into the calculation stage. This means a smoother, more efficient workflow right from the start. By optionally incorporating the power of Virtual Machine during the initial toolpath generation, potential collisions can be detected and resolved early in the programming process. The result is fewer surprises down the line and no waiting around while the machine waits for correct code. Catching issues early leads to faster and more reliable machining, and of course, safer automation. So, enough about the current situation of CAM. How about the future? Well, obviously I can't divulge too much information on what we're working on, but I can confidently say that AI and the use of large database models of information will be a big part of what we do in the future. Maybe it's just searching through a database of previously programmed parts for similar features, and then applying proven strategies from those features on a new part. Or maybe it's a scenario where AI can look at a model fixture and calculates rigidity, and perhaps even do that with cutting tools, and then automatically suggest speeds and feeds accordingly. I'm sure some of the best ideas haven't even been thought of yet, but isn't that what makes the future exciting? Okay, to wrap this up, I'd like to just finish on another quote I read somewhere, just so everyone realizes that AI and automation need not be something to fear. Much like any tool that's available to us, it can be used as much or as little as possible. And if used correctly, it can make our lives easier, more powerful, or perhaps even both. Pushing the boundaries of toolpath development is an ongoing journey, driven by innovation, curiosity, and great ideas. And even as we automate more of the CAM process, the human element remains vital. Creativity, intuition, and fresh thinking will always have a place in this evolution. Remember, we're not approaching the end of CAM development. We have really only just begun. And it's clear that new and clever ways of doing things will only make automation a more powerful tool for programmers everywhere. And to wrap this up, at OpenMind, our passion is CAM, and the future is just getting started. Thank you for listening. I hope everyone got something out of this, and if not, I hope you at least found it somewhat entertaining. Also, feel free to call, email, or reach out to me on LinkedIn. I would love to hear your thoughts on AI, automation, and the future of CAM programming. Thanks again, and goodbye.
Awesome. So we are glad to be joined by Ernie himself after that presentation. Thank you so much for your time and your expertise today, Ernie. We do have some questions rolling in from the audience. So what do you say we get started?
Let's do it.
Awesome. So Jason wants to know, what about robot-based material removal and machining? What is OpenMind doing in that space?
Okay, good question. So with robots, it's a little bit of a different situation. What we're doing is actually taking our toolpaths and the vectors from those toolpaths and the code, and then using usually a third-party translator that converts the data from, that information to something a robot can read. So technically, we're not doing anything unique or different in that world, but we do have many users machining on robots and actually doing additive work on robots as well, essentially taking our tool paths, porting those through this third-party software, and there's a couple of them out there, and then putting that into a robot.
Awesome. So also it looks like Danny wants to know, I run a shop or a job shop with different parts every day. Would automation even be worth it to me?
I mean, that was my background as well. So automation at first was like, what is this? I don't need this. But the reality is there's certain things that everybody does all the time, right? Whether it's drill holes or maybe just starting a new CAM project where you just want to, put a stock on there, put the stock into a vise, have the vise automatically close, set your zero automatically. So if you have a good scalable automation solution, you really can use it as little or as much as you want, right? So, it's not going to replace all your programmers. It's not going to probably replace any programmers because, well, as we all know, programmers are kind of hard to find nowadays. So having that ability to use it just a little bit or use it a lot or both, it sort of makes it a powerful tool for a lot of people.
Awesome. So also Carlos wants to know your thoughts on metal 3D printing. Is it kind of a competitor to you? What are your thoughts of, working with 3D metal printing compared to what you guys are doing at OpenMind?
You should check out our webpage. We have a whole section on additive. We're doing a lot of work in the additive space. Is it a competitor? Well, no, because we're working in it.
Yeah.
Is it a replacement for metal removal? No, I think it's just complementary, right? So there's certainly places where that is the right choice, and there's certainly places where old-fashioned milling and turning and EDM work still makes sense. So
awesome. A few more here, Ernie. Looks like Pat wants to know or says, I have many years of programmed parts. Can I capture that knowledge and work while implementing it into automation?
For us, I can't speak for other CAM providers, but for us, not a problem. There was that point in the presentation where I spoke about features and macros. The feature or the macros, I should say, are essentially just the toolpaths. So you could actually take those toolpaths, save those into our macro database, and apply those into the automation. So all that data, all that knowledge is still extremely important. And having the ability to easily capture that, then port that into some sort of automation tool is there and important.
Gotcha. And looks like Brian says, I have solid programming team already. How could automation help make that difference? Also, how do I sell it to them if they feel insecure about their jobs?
I mean, we're all going through this, right?
Yeah.
What's the future hold? Are we all going to be replaced by robots and AI? Maybe, maybe 100 years from now, I don't know, 50 years from now, but now, I feel like all this automation is just making our lives easier. I sort of touched on this on on the second question that, there's a lot of little places that you don't think you need it, that it could be really
Mhm.
powerful. And the one thing that it does is it makes us more efficient, right?
Yeah.
So the mundane stuff that we don't like, let the automation do that. The fun, challenging, the stuff that actually makes a lot of money, well, that's the stuff where the humans still have to touch for now, anyways. So, yeah, that's how I would sell it. If I owned a shop, I would say, listen, we're not replacing you because one,
Mhm.
there's not many of you out there to begin with, and two, we just want you to focus on the hard stuff and the challenging stuff because we believe you're good at what you do. And I think people like that. People want to be appreciated, and they want the tools to make the easy stuff easy, right?
Yeah.
So.
Well, I'm bought in. So that looks like it just about wraps things up. I mean, if anyone does have any more questions for Ernie, you can send them in. But if not, I just wanted to say thank you very much to Open Mind Technologies for sponsoring today's Lunch and Learn. And obviously, a massive thank you to Ernie Dickinson for your time and your expertise today. I hope you have a great rest of your day, Ernie.
Thank you.
You can listen to all of our episodes of Manufacturing Matters and Lunch and Learn podcast from the MFG Radio Network on Spotify, Apple Music, and on our websites, todaysmedicaldevelopments.com, aerospacemanufacturinganddesign.com, defenseandmunitions.com, and evdesignandmanufacturing.com.